Hello. The mathematics of finite sets and RSA, a modern crypto method, is the focus in this lecture. So let's get started. So mathematics, and in particular number theory, plays a key role in modern cryptography. So while in mathematics, the understanding of mathematics, in particular understanding of modular arithmetic, is key to understanding modern crypto methods. So, for example, if you're given a message and you want to encrypt that message by raising it to power some key, which is E, and you're sending this message ME, and the receiver should be able to decode this message. And the encryption and decryption require an understanding of the modular arithmetic. So we'll learn that using modular arithmetic, we can make large computations more manageable. So this requires the understanding of an area of mathematics called number theory. So number theory is devoted to the study of the mathematics of the integers. As we know, the integers are infinite, but in this case, we're going to focus on a very large set of a finite set of integers with certain properties. So first we start with some definitions. We say that A divides B if there's an integer such that B is equal to AC. We can give a lot of examples of that. We know that 3 divides 12 because we can write 12 as 3 times 4. So we use the notation A vertical bar to denote that. This is not the fraction notation. This says that A divides B. So division of linear combinations, if A divides B and A divides C, then A also divides any linear combinations. For example, we know 3 divides 12 and we know 3 divides 15, and this implies that 3 divides 12, m plus 15. So the division algorithm is focused on if A is an integer and D is a positive integer, then there are unique integers Q and R such that R is between D and 0, and this relationship is satisfied. You might recognize this as a familiar algorithm. So for example, if you take 19 and if you divide 19 by 7, you will have a quotient of 2 and a remainder of 5. So notice that 5 is between 7 and 0. So this is Q and this is R. But this is a more general definition of division. For example, you can just say there's a relation between minus 19 and 7. So for instance, if I say 7 times negative 3, which gives you negative 21, plus 2 also has satisfied that relationship. So in this case, we can say Q is equal to negative 3 and the R is equal to 2. Notice that in this definition, only the D and the R has to be positive. A and Q can be negative, as you see in this example. The congruence relationship is that we say A is congruent to B mod M if M divides A minus B. We can show that if M divides A minus B, M also divides B minus A. So we see this relation that 45 is congruent to 0 mod 9. This means that 9 divides 45 minus 0. We can extend that and say 46 is congruent to 1 mod 9. So in this case, what we say is 46 minus 1 is divisible by 9. Or we can say 47 is congruent to 2, and so on. So in terms of equivalence classes, we say that 45 and 0 are in the same class, or 46 and 1 are in the same class. The usefulness of this theorem is that you can replace 46 by 1 in a computation. For example, if you want to do 46 to the power 27, modulo 9, that would be the same as 1 to the power 27 modulo 9, which is much easier to do. Now, mathematics of finite sets deal with this special set called Zm, which is the set of all the integers from 0 to m minus 1. Now, if you imagine that m equals 12, you might recognize this as a clock numbers. So the clock goes from 0 to 11 and then gets back to 0 when it hits 12 again. So we also know that we can write 13, a relation between 13 and 12. 13 is congruent to 1 mod 12. So we can say that in a clock, the hour 13 is the same as hour 1. So here are some examples of modular classes. If you assume that m equals 5, then 0 is congruent to all of these things because you can take the difference between 0 and any one of them, and it's divisible by 5. And you can take even elements from here. You can take 5 and 10. Minus 5 minus 10 is divisible by 5. If you take the class 1, it concludes 1, 6, 11, and so on. You might recognize this as just adding 1 to the previous one. So this also makes sense because 1 minus 1, which is 0, divisible by 5. 1 minus 6 is 5, or minus 5, divisible by 5, and so on. So not only there's a relation between 1 and all of these numbers, but there's also a relationship between these. In other words, the class of 6 is the same as class of 11. So here's a class of 2, here's a class of 3, here's a class of 4. But when you go back to 5, you're getting back to the same class. In other words, 5 and 0 are in the same class. So if A is congruent to B, then A and B are in the same class. So here's an example of the use of equivalence classes to solve something that might seem very difficult. So suppose we want to take 12 to the power 8 mod 5. Now, obviously, in real life, we're going to be dealing with much, much larger numbers. So we recognize that in the modulo 5 arithmetic, 2 and 12 are in the same class as same class. So this means 12 is in 2, and therefore problem of finding 12 to the 8 mod 5 reduces to problem of finding 2 to the 8 mod 5. Because 2 to the 8 mod 5 is 256 mod 5, which we know to be 1, we can claim that the answer to this question is also 1. So let's talk about the greatest common divisor first. Greatest common divisor is the largest common factor that divides both A and B. So for example, greatest common divisor of 2 and 5 is 1. Greatest common divisor of 5 and 7 is 11. But if you find the GCD of, say, 12 and 15, the largest number that divides is 3. So, and the greatest common divisor is very important. And if the greatest common divisor between two numbers is 1, we call that they are relatively prime. And this notion is really important for the next idea. If n is a positive integer and k is relatively prime to n, then we can find an integer k inverse. Now this inverse is not the same as what you learned in algebra. Because in algebra we learned that given 2, and 2 inverse is like 1/2. If you multiply them, you get 1. But the problem in modular arithmetic is, although 2 is an integer, 1/2 is not an integer. So what we're looking for is two integers whose product is congruent to 1 mod n. So let's take a look at this example here. GCD of 2 and 5 is 1, and therefore we will be able to find an inverse of 2 in the modular 5 arithmetic. Now we notice that 2 times 3 is 1 congruent to 1 mod 5, which means 6 minus 1 is divisible by 5. Therefore we claim that 3 is the inverse of 2. That means 3 times 2 is congruent to 1 mod 5. If 3 is the inverse of 2, 2 is the inverse of 3. Now there are other properties of this integer ring. In other words, given A, you can always find another one, B, such that the sum is 0. So for example, if you take 5 plus 2 is congruent to 0 mod 7, for example, right? So we have, this is 7, which is 7 minus 0 is divisible by 7. So we can find some other b. So in this case, we say the additive inverse of 5 is 2, and the additive inverse of 2 is 5. You might be able to find more than one additive inverse for a given number. We can also find multiplicative inverse. In other words, given a, there are some, for some a, not for all, unlike this one, for all. In this case, it's some, because a has to be relatively prime to m in order to find a multiplicative inverse. There are other properties of this integer ring Zm, which means that it's closed under addition and multiplication, which means that if a and b are there, then a plus b is there, and a times b is there. All these numbers in this ring satisfy the associative and multiplication, associative property for addition and multiplication. For every element in A, if you add a 0, you get the same element back, which is a property of integers as well. For every integer, we can find another integer minus a, which is equal to that. Now notice in this case, this minus a is not the same as what we think of minus a. This minus a could be something like, say, if you have 2 plus 3 is congruent to 0 mod 5. So this is the minus 2, really, and that's the negative additive inverse of 2. Or we can think of this as the minus 3. That's the additive inverse of 3. So let's look at the advanced crypto methods and how this might work. So the main idea of advanced crypto method, or the RSA motivation, is that we have the original text, and there's a public key for A. A is the one who is receiving the message. The B encrypt the message using A's public key. And the resulting text is called ciphertext, and this text is the one that an intruder cannot understand unless the intruder gets hold of A's private key. So using A's private key, A will decrypt this and get the original text back. So that's the key idea of this public-private encryption. Now, in practice, these keys are much, much large, and you can see this is a very, very long key shown in hexadecimal notation. This is a public key and a private key here. And there are a number of programs that can generate these keys on demand. So how RSA works, the receiver has both private key, which they guard closely, and a public key, which they distribute to anyone who wants to send a message to the receiver. A sender wishing to transmit a secret message to the receiver have to encrypt the message using the receiver's widely distributed public key. The receiver can then decrypt the received message using the closely held private key. So the process goes like this. Given two distinct primes, typically we take very large primes, probably about 200 digits, and then we multiply them to create an integer called n, which is the product of two primes. So if p and q are both 200 digits long, p times q would be about 400 digits long. So we are talking about very, very large numbers in the order of 10 to the 400. That's 400 zeros in there. Then we select an integer e in this range such that the GCD of e and p minus 1, q minus 1 is 0. And this e is the one we call the public pair. We'll do an example to understand how this might work. Then we have to compute d such that d is the inverse of e. This means that d times e must be 1 mod p minus 1, q minus 1. And the private key pair is called dn. So this is the one that the receiver keeps secret. So when you want to send a message, you take the message and raise that to the power the encryption key, which is a public key, and send the message to the receiver. So receiver get the message m star. So the receiver take the message m star and use the private decryption key to figure out what the message is. So how do we know what this works? So we'll take a look at this next. So in the workshop, we want to, given two primes, we want to generate public and private key pairs. Obviously, this is an example with small numbers, or small primes. So it doesn't really include all the things that we want to do. So let's see how this might work. So first we find n, which is the product of the two primes, that's 35. Then we want to find a number which is relatively prime to p minus 1, q minus 1 product. So in this case, 24. So we find an e such that GCD of E24 is 1. So in this case, we choose e to be 5. So now they have the public key pair, which is e, which is 5, and 35 is the product of the two primes. So we are publishing this as the public key pair. So anyone who wants to send the receiver message have to use this to encrypt that. And the decryption is done like this. Given this e, we want to find a d such that e times d is congruent to 1 mod 24. In this case, we choose d to be 5. So if you look at this, e is 5, d is 5, so 5 times 5 is 25, minus 1 is 24, this is divisible by 24. This means e times d is congruent to 1 mod 24. So the private key pair is dn is 535. In this case, it turns out to be e and d are the same, but it doesn't have to be the same. So how this works? So let's take a look at how this might work. Suppose you want to send the message 2, and your encryption key is 5. And so the encrypted message is going to be 2 to the 5, which is in fact 32. And we do this in the modulo 35, so 32 is still 32. And then we send the message to the receiver, and the receiver take the message and raise that to the decrypt key, which is 5. But that's a large number, and we want to find out what is this equal to in the modular 35 arithmetic. But one interesting thing we could do is that we know that 32 and minus 3 are in the same class, because 32 minus 3 is 35, which is divisible by 35. So they're in the same class. And therefore, we might replace 32 by minus 3. So we can write this as minus 3 to the 5. We want to find some key to match that. But minus 3 to the 5 is equal to minus 243. And we know the following. We know that minus 243 is congruent to 2 mod 35. How do we know that? Because if you take 243 minus 2, which is 245, that's divisible by 35. And therefore, here's the message. So we start with the message 2. We send the encrypted message to the user, which is the receiver, which is 32. And the receiver took the encrypted message and raised that to the decrypt key here and found some very large number. But because we didn't want to do the large number, we picked some other number in the same class, which is minus 3. And then we took, instead of taking 32 to the 5, we took minus 3 to the 5, which turns out to be 243. But then we have to find something that's congruent to in the modulo 35. So we found out that minus 243, in fact, is congruent to 2 mod 35. So therefore, we have the message received. So why RSA is hard to break? Because prime factorization is very hard. We are talking about numbers that are very large, in 400 digits in length. Although you know n and e, which are public, you cannot find d using this information in a reasonable time. So if you're interested, you can read more about what primes are found so far. And the largest prime that was found, it was in 2013, and they are still working. These computers are constantly running, looking for the next prime. They haven't found the next prime yet. So this is the end of the RSA lecture.